Right, for the second morning talk, we'll have different ones from here faculty. It's going to talk about Fission category symmetries and anomalies.
Okay, thanks for the introduction, and thanks for the opportunity to speak here on some past work I've done with Jimin Chang, Xuanbing, Shuhen Xiao, and see in the audience, and some upcoming exciting work with Ryan, who's also in the audience. So as the title suggests, I'll be talking about symmetries, but a new kind of symmetries, which is related to Fission categories, and then we'll talk about anomalies associated with such symmetries. As you have all seen from this nice workshop, the power of symmetry is immense. Symmetry has played an important role in understanding QFTs, generally understanding, for example, understanding RG flows of given quantum field theory, understanding various phases in your phase diagram, and duality speaking different description of the same quantum field theory. Okay? And in this kind of story, an important ingredient of symmetry is the presence of Topf anomalies. And whenever you have a Topf anomaly, you can make very strong assertions about what kind of dynamics the quantum field theory may have. There's a recent reformulation, elegant reformulation of symmetries by topological defects. This was due to this paper from Kapuskin, Seiberg, and Willett in 2015, where symmetry generators can be phrased as topological defects, and they also give higher form generalization of the usual zero form symmetries. But once you have formulated symmetry as topological defects, there's a natural extension. So first, we have to recall that symmetry defects are all like group-like. So in particular, the fusion of the defects obey the group law, which implies that symmetry generators are invertible. So the natural extension is to consider non-invertible but still topological defects. Okay? And then once you understand there's such a notion, then you can ask, is there some extension of anomaly for this non-invertible topological defects? And another interesting question will be, are there new gapped phases which are protected by these non-invertible topological defects, which are beyond the usual symmetry protected phases that we know about? Okay? So in this talk, in order to make progress, this kind of question you can ask in general dimensions, but in order to make progress, I'll focus on 1+1 dimension in this talk. Okay, so the plan of the talk is going to be, I'll first introduce to you about topological defect lines in 1+1 dimension CFDs. It'll probably be a review for many of you. And then I'll talk about the connection to Fission category symmetries, which formalize such topological defect lines in a mathematical language. And then I'll introduce to you the notion of anomaly for Fission category symmetries, and I'll show how they can play an important role in constraining RG flows and various phases of a given QFT. And then I'll give you, along the way, I'll give you some examples for illustration of the ideas, and I'll end with some conclusion and some output. Okay, so let's start with some basic axioms of the topological defect line in the 1+1 dimensional quantum field theory, or quantum field theory, which I focus on in this section. So the first basic axiom is that this defect line is supposed to be topological. So imagine you have this defect line, and you have some local operator insertions. Then you can freely deform the defect line without changing the observable. So you're supposed to think about this thing as a little patch of your full observable, which may involve other defect lines as well as other operator insertions. So this kind of deforming the defect line without crossing this local operator does not change the observable. That's the notion of topological invariance. And another important axiom associated with topological defect lines is the presence of a defect hyperspace, which basically allows you to cut open this topological defects and insert a complete set of space. Okay? And so if you in the CFT, if you have this defect line inserted in the time direction, in the radial direction if you're on the plane, or in the time direction if you're on the cylinder, then the hyperspace is associated with the circle with this defect point inserted. Okay? And another important ingredient of defining topological defect lines in 1+ dimensional CFTs are the notion of topological junctions. So the defect lines, they can join at topological junctions. They're topological in the sense that you can move around the junction without crossing the other operators, without changing the observable. Again, you should think about this as a local patch of your full observable. So these O's are going to be some type of this defect operators, which end on this lines L1, 2, 3. I think the diagram is a bit small. hopefully you can see. And the V labels the type of topological junctions you may have. So in general, there could be multiple topological junctions associated with 3 species of incoming lines or outgoing lines in this case. Okay. So some other important axiom, of course, is the fusion, which is similar to what you encountered in the symmetry defect case, where in that case you have the fusion of the group-like defects which furnish a representation of your group symmetry algebra. So in this case, you get some you have something similar. And another interesting important notion is crossing. So whenever you have a defect network of this type, which involve 4 external lines, topological lines, and they fuse and join into some other external lines and split, you can replace this picture by this picture at the cost of introducing what's known as the F symbol or F matrix, or sometimes also known as crossing curve. And lastly, because we won't have the 1+1 dimensional CFT to be well-defined only Riemann surface of arbitrary keenness, an important notion is the Moser invariance, or covariance rather. We have other operator insertions, which basically says that doing an S transform is equivalent to rotating the picture by 90 degrees. And you have to, if you have local operator insertion, you have to insert appropriate phases. Okay. So in this talk, I'll abbreviate topological defect lines made by TPLs. These are the only interesting defects in 1+1 dimension. Okay. So this kind of axioms, which are natural from the CFT perspective, has a very natural formulation in the mathematics. This is known as the fusion category. What is a fusion category? The fusion category is just a categorification of a fusion ring, which is, you can think of as some algebra where the relations only involve positive integer coefficients. And the fusion category is start with a fusion ring, and you enrich it by F symbols, which are essentially crossing kernels, that are subject to the Pentagon equation. So if I give you a fusion ring, the task of defining the fusion category is to find F symbols which solve the Pentagon equation, and that's all.
Question?
Yes.
We need not be fusion rules.
It doesn't have to be graded.
And also symmetric. That's
You mean dual?
A cross B is B cross A.
It doesn't have to be. Yeah. So the important point is that fusion category doesn't have to be graded. And it doesn't have to be symmetric. For example, the case of a non-Wheeling group-like algebra would be such a case. But there are more sophisticated examples like the half E6, which is a rank 3 fusion category. That's also not graded. But in that case, it's complicated.
Which one's it?
Half E6. Okay. Yeah, I can take it afterwards. Yeah. So what are some general features of topological defect lines? As you might have imagined, as for group-like defects, the defect lines will be able to act on local operators. So imagine you have a picture where you have this topological defect line labeled by L, and you have some local operator insertion. And if the local operator insertion is charged under this defect, similar to the group-like symmetry case, then this operation can be represented as this L, the action of this defect line acting on the local operator. If the operator is not charged on the L, then you can freely move this operator outside the defect. And you can shrink the as well if you wish. Okay. And then TPLs also satisfy interesting modular bootstrap equation constraints. So this basically comes from the modular covariance, or modular invariance axiom, which I presented on the previous slide. So if you have some configuration of network of topological defect lines, say suppose you have this, think about this as on the torus where the opposite sides are identified. This kind of relation will give you a relation between the twisted partition function on the torus by the defect network. And because this defects are topological, they commute with both your left and right moving Virasoro algebras. You can expand the twisted partition function in terms of Virasoro characters, where the coefficient would correspond to basically the action of this defect network. So for example, in this picture, you can think about this defect network. If you think about this as time direction, you can think about this defect network as computing some twisted partition function in the Hilbert space associated with this defect line L1. Okay? And this picture will be the twisted partition function in the Hilbert space associated with defect line L2. Okay? And this kind of using this kind of expansion and this relation, it will give strong constraints on how this defect lines can act. These are some matrices. And another important feature of this topological defect lines are they're rather rigid. So this is in the mathematical literature, this is known as the Oceano rigidity, which basically says that the defect lines, the set of topological defect lines which furnish Fission category does not have any continuous deformations, which is kind of natural because of the fact that they rise from solving some polynomial equation like Pentagon equations. So you typically expect, you only expect the discrete set of solution, so they should not change on origin. And here, of course, to make this statement, you have to assume that defects commutes with your relevant perturbation, which you turn on to trigger the RG flow, and that corresponds to, in this special case where in this picture, that the defect acting on the operator is equivalent to pulling out the operator, which after shrinking the defect, you just pick up the bed, which is also known as the quantum definition. All right. So that's some general feature of DDLs, and then you can ask, do we see them in CFTs? And indeed, we see them very often in CFTs. So they show up in several different ways and several different manifestations. One simple way to realize them is as Valente-like lines in RCFTs. In this case, these are lines which are in one-to-one correspondence with the chiral primaries in a theory, and they act diagonally on the chiral primaries. So in the sense that they actually compute with the enhanced chiral algebra, which includes the Virasoro algebra as a subalgebra. And these Valente lines, their F symbols and all their data are just fixed by the Moore-Seiberg data associated with RCFT, or equivalently the modular tensor gallery data. And another place where this topological defect line shows up is as Wilson lines. Whenever you're 1+1 dimensional theory or Coulomb field theory or CFT, that's some gauge theory description, some discrete gauge theory description. So one simple example is the presence of this red S3 Fission category that shows in tetrahedral icing, and this can be derived quickly by realizing that tetrahedral icing is equivalent to 3-state paths folded by S3 symmetry. So if you start from 3-state paths and you gauge the S3, you get tetrahedral icing, then naturally you have red S3 as topological defect lines in this theory. Okay. Another place this defect line shows up are these duality lines, and the famous example is the Kramer-Schweiner duality in icing CFT. In that case, you have 3 lines, which I'll say more about, and the sigma primary, the spin primary, is corresponds to the duality line.
What do you need rationality in the first case?
Sorry?
What do you need rationality in the first case?
Because this is Valente lines is only defined for rational CFT in the sense I'm describing.
Why can't I still just take any chiral primary and have it multiply every other chiral primary even if there are infinitely many of them?
You can, but because in that case you have to make sure that you have a solution to the F symbols. I'm saying here the modular tensor category data give you a solution automatically. You don't have to do any work.
Okay, so you're just saying like the answer is that
yes.
Is the answer you would get like in the end.
Yeah. So I'm saying these are simple realization, but of course CFT has multiple realizations as we suggested. So in principle in rational CFT they also show up, but we don't have this simple description like this. Okay, so this is the physics side of this topological defect lines or Fission categories. What about the mathematical side? So the simplest the math problem you can imagine is to start from a fusion ring. So for example, this simplest case, you have a single non-trivial object in your fusion ring, which is X, and it squares to some combination of infinity, which is a trivial defect line, and the X itself. Okay, and the task is to solve for the F symbols using the Pentagon relations. This kind of problem was formulated by Ian Ho. So this is very simple. So this is a simple-looking question, and for this particular case, you can find the answer. It requires some work, but the answer is surprising in some sense. Okay. So the first point is the answer only exists for a equal to 0 or 1. So the fusion ring is perfectly well defined. It's integral and it's positive for a bigger than 1, but there's no solution to the Pentagon equation if a is bigger than 1. Second of all, if a equal to 0, you actually find 2 solutions. And the 2 solutions are simply corresponding to the 2 symmetry Z2 categories. and the actual label alpha comes from the cocycle that labels the total anomaly for the Z2 symmetry line. Okay. And for A2 you get an interesting solution. You again get two solutions, and they correspond to the Fibonacci category, where the quantum dimension of this non-trivial defect could be either the Golden ratio or the 1 minus square root of 5 over 2 partner. And in one case, the quantum dimension is positive, the other case is negative. In charity, actually requires the quantum dimension to be always positive. And so the unitary version is actually realized in, for example, the tricritical IC model, steady state class model, and so on. And the non-unitary version is the Fermi one that realized that beyond CFT to come up. What about the general case? Well, more generally, as explored by, so this is the incomplete list of references here, as explored by this gentleman, the complete classification to date seems to be out of reach. Of course, this generalized the notion of classification of finite groups as a very special case. And people have tried to attempt classification case by case based on the rank. So the rank of the Turing category just tells you how many simple TBLs you have in the category. And no classification has been done up to rank 3. And at rank 3, there are 5 fusion rings, which have solution to the Pentagon equations. And if you solve the Pentagon equation, you have 15 solutions, and they're all listed. And they include, in particular, the case of D3 symmetry. So the D3 symmetry has order 3, so naturally it's give you a rank 3 fusion category. But they also have, but all the other cases all have realization in RCFTs, like Canino models or Takuzi-Dato models or various cosets. So already at rank 4, the classification goes wild, like in the sense that it's not known whether you have a finite set of fusion rings which are compatible with the Pentagon equations, and there's no control. People try to make progress by putting an additional constraint on fusion categories, such as braid structure or modular tensor category. And in those special cases, there are classification. But in the general case of fusion categories at rank 4, there's no classification option. Okay. So so these are some abstract ideas. So let me now illustrate this using the simple example of the Ising CFT. So in Ising CFT, the fusion category or the set of these topological defect lines are sometimes referred to the Tabari-Yamagami category associated with Z2 symmetry, which I'll say a little more in a bit. So in this case, the topological defect line are E1 corresponding with the primaries in the CFT, the identity energy operator is spin operator, and these are correspond to defect lines. The fusion rule of the defect lines are determined by the fusion rule of the primaries, because these are related like defects as follows. So for example, the eta is the usual Z2 symmetry generator, so they satisfy the expected fusion rule. The absent are particularly simple. It just tells you that if we have this, so the blue line, the duality defect line n, and the red line are the symmetry defect eta. And when you do this kind of F move, you pack on that sign. Okay? And in the case of when you have 2 duality defects, you can do this crossing at the cost of introducing some symmetry effect that connected these two lines. Okay. And this defect operators, and this duality line implements the Kramer-Wagner duality in the sense that when you have this duality line and you have the spin operator sigma on one side, if you put it to the other side, what you end up with is a non-local operator, the disorder operator mu attached to the symmetry eta. So the mu operator is a special example of a defect operator that lives in the Hilbert space with a defect point given by the transverse given by the transverse eta symmetry defect. All right. So with that example in mind, let me now introduce to you the notion of anomaly for fusion category, or what's the notion of anomalous fusion category. Okay? So there has not been such a definition in the literature before, so this is going to be our definition. So our definition is that the fusion category symmetry A, curly A, is anomalous if and only if there's no asymmetric non-degenerate gap space, which I'll define later. With this statement, then anomalous A necessarily enforces that the IR phase has to be either a CFT or gapless phase, or some symmetry breaking phase that breaks this fusion category symmetry currently. Okay? And of course, as you may imagine, a generalized ordinary symmetry phase has a special subphase.
Symmetry is not necessary.
Yeah, so the symmetry, fusion category symmetry means that, so it's not group symmetry. In the invertible case, it corresponds to group symmetry, but it's far more general. All right, so there's no pass. So the very simple theorem you can derive just from the axioms that I present in the beginning of this talk is the following. So if the quantum dimension of the defect line is not integral, then any IR phase triggered by relevant deformation that commutes with this defect cannot end up with a tributary gap phase or symmetric non-degenerate gap phase. So this is the simple argument you can do in your head by comparing the two-dependent function with the defect line inserted in the spatial direction versus the twisted torus-dependent function with the defect line inserted in the time direction. So because you are in the gap, assuming you are in the non-degenerate gap phase, you have a single vacuum in the block. Then the left-hand side will give you just give you the quantum dimension of the defect line, and the right-hand side will give you the dimension of the defect Hilbert space associated with the defect line. So the defect line here is in the time direction, here is in the spatial direction, and this will tell you that the defect line's quantum dimension has to be integral, and that will be in contradiction if you have a triply non-degenerate gap space. Okay. So this is proved by contradiction. So with this simple theorem in mind, there are already powerful consequences. So let me show you this, illustrate this in an example. So the example will be the tricycle Ising CFD. So this is the 4,5 millimodel at center charge 7/10. This theory has 7 primaries. It has 3 energy operators and 2 spin operators. And there are corresponding related like DB output defect lines, which are labeled as follows. This eta generates the C2 global symmetry of the tricycle Ising model. And this cardiac N is going to give you some sub-Ising category generated like this. And this W generated the interesting Fibonacci category, W squared. And now you can look for operators in this theory that trigger RG flows while preserving a subset of the fusion category. A subcategory in the fusion category, or a subset of the TPLs. One such interesting deformation is this sigma prime spin operator, which has dimension 7/8. So relevant deformation that preserve the Fibonacci category, which you can work out using the Morse algorithm data. And another interesting deformation is this energy deformation, which is also relevant and preserve the Ising category. Okay? As we saw on the last slide, we have this theorem, which says that if the quantum dimension of the defect line commuting with the relevant deformation is not integral, then our phase cannot be triply gapped. So here, both Fibonacci and Ising has topological defect lines which have fractal quantum dimensions. In the Ising case, it's square root 2. In the Fibonacci case, it's the golden ratio. So, the R phase cannot be triply gapped. Okay? So that's a prediction. And then you can check it using other methods such as integrable flows and also the truncated conformal space approach, which is related to what Steve talked about in the last talk. And it was shown that for this spin operator deformation, indeed, well, either sign, because you have a Z2 symmetry, so sign doesn't matter, you get a doubly degenerate ground state, okay, so which is not the non-degenerate gap symmetric phase. And for the energy operator, now the sign make a difference. In one sign, you get Ising CFD, which naturally realizes Ising category, Ising mask. And with the negative sign, you get triply degenerate ground state, which also give you a phase that's consistent with the Ising category symmetry. Okay. So the simple theorem requires having some topological defect line with fractional quantum dimensions. But there are a lot more fusion categories which are integral in the sense that all the quantum dimension integer. So the natural question is that for these cases, there are still interesting theorems we can make about constraining RG flows using the category symmetry? The answer is yes. So this is based on the upcoming work with Brian. So we present a general theorem which says that the fusion category A has symmetric non-genetic gap states of fusion category symmetry A are in multiple corresponding with the fiber functors of A. So you don't have to be scared about this terminology. I'll explain what it means in the physics context. So So the fiber functor, or equivalently a symmetric non-degenerate gap space, in this talk will just be the following data. So you assign, it's essentially extended 2D to QFT where we have a single ground state in the bulk. So if you cut it open, there's only a single ground state. But there's a non-trivial defect Hilbert space associated with each TBL. In particular, the dimension of each defect Hilbert space is fixed to be the quantum dimension of that defect line. Okay? This is basically derived from the Gaussian invariance, with the defect line inserted in the time circle versus the spatial circle. And then you have this defect 3-point function. So suppose you normalize the 2-point functions of the defect operators, OA at one end of the defect line LA, and also on the other ends. Then you have this interesting unambiguous observable like this, okay? And so okay, this is me. And there's a constraint. The constraint of the defines the fiber functor boils simply down to the consistent of cutting and gluing in this picture. Okay? So if you have this defect 4-point function, you cut in this way, and you basically get a polynomial of degree 2 in this mu. But you can use the F move to get this picture, and you can cut it open in a different way, so you can get some quadratic polynomial in the mu. And this gives you some constraint on mu. But in the physics context, it's simply just coming from the cutting and gluing consistent functions. Okay, so to illustrate some of these ideas, let me go back to the Tabarami categories which generalize the Ising category. So the simplest way to generalize is to just replace Z2 by any abelian symmetry. And this is going to be a category that's going to be some Z2-like extension of the symmetry algebra G. So you just introduce another duality effect N. And in particular, the quantum dimension N is going to be the square root of the order of the group, which can be integral. Okay. And the fusion data determines some bi-character and some sign, which is associated with the Frobenius Shor indicator of the duality effect. And the bi-character determines that symbol in the following ways. And the symbol consequence of the fact, whenever you have the CFT that realizes the duality defect, a symbol consequence of the CFT, the corresponding CFT, has to be self-dual or equivalent to its G-gauged partner. Okay? So the Ising case is a special case of this. So let's illustrate this in the case of Ising squared CFT. So Ising squared CFT is center chart 1, and this theory has D8 global symmetry. Of course, it contains the Tabarami category associated with the Ising subvectors. The Ising subvectors. But it has a lot more. It has a much richer set of duality defect lines. For example, we realized the Tabarami category associated with Z2 times Z2 symmetry, as you may expect. Also with Z4 symmetry. These are both subgroups of D8. Okay? And if you look at study S symbols, you see that we actually realize different Tabarami categories associated with Z2 times Z2 and Z4, labeled by the back characters chi, S, and A, and it's not very important. What's important here is that if you study the fiber functors associated with this category, you find that for this case, there's a single fiber functor associated with of some hopeful algebra. And in this case, you get 3 fiber functors associated with some gauge theory, descriptive gauge theory with D8 symmetry, gauge symmetry. And in other cases, you have no fiber functors. And the important thing to note is that all these categories, all 4 of them are preserved, not this one. All 4 of them are preserved by the energy of deformation, which are symmetric, which preserve the category symmetries. And so as a consequence, this fusion category will persist on the entire C1 orbital branch at arbitrary rational radius. So this presence of this fusion category, as I said on the last slide, implies that the Dash-Tanner model is self-dual under Z4 or Z2 times 2 Z2 gauge, okay, on the entire orbital branch. And on the generic generic point on the orbital branch, with some radius of the orbifolded boson, there do exist relevant deformations which preserve the category symmetries. And in those cases, you turn on the deformation, it will drive. You can show explicitly that the theory will be driven to the spontaneous symmetry breaking phase, as required by the absence of fiber functors for these 2 fusion categories. All right, so let me just summarize. Minus 1 minute. Okay. The punchline here is I want to convey to you is that non-invertible defects are as important as invertible topological defects. They share many features. In particular, there's a notion of anomaly for non-invertible defects, and they play a powerful role in constraining dynamics. For example, can forbid RG flows to trivially gapped spaces. And there can also be interesting new kind of SPTs, which in my talk associated with fiber functors of these fusion categories. These are SPTs protected by this fusion category symmetries, which cannot be distinguished, which otherwise cannot be distinguished by just the symmetry, usual symmetry protected. Symmetry. SPT associated with group-like symmetries. Okay, so what I didn't get to talk about is the connection to behavioral theories and the living wing model, where this theory shows out some boundary conditions. The 2D CFT shows some boundary condition. Also, the connection to Anion chain, and also more general category symmetric phases, which can be degenerate in terms of module categories associated with the fusion category. And what I also didn't talk about are some new fusion categories, interesting fusion categories we find with Ryan in C2 and CFT, also with triality and tetraality and ultimate comes. Okay. And also I didn't talk about is some new category protected symmetric SPTs from discrete gauge theory in one-plus dimension, for example, in the RAP-DA theory. And you can show that there are non-trivial edge states between this different kind of ASPTs, which are indistinguishable otherwise as usual SPTs. And some interesting future directions involved, just as this during his talk, are non-invertible defects in massive theories. The simple example is to look for integrable defects along integral flows, but there are also other generalizations. And another interesting generalization, which is about, of course, about non-invertible defects in higher dimensions. These defects are known to exist. Simple example is due to the paper of Kapustin and Salina as surface operators in the U1 level A transaminase theory. In that case, you have 3 non-trivial simple topological defects. And they furnish the following fusion pool. To note, here the defects S2 is not dualizable in the sense that the identity does not appear in the fusion of 2 S2s. So in this sense, this does not define a usual fusion category, but there may be some other structure that govern the splitting crossing of these defects. And it will be interesting to see whether such defects, if you constraint, are interacting transaminase theory in 3 dimensions and also generalizations. Thank you.
If you have a trivially gapped phase realizing some fusion category symmetry corresponding to a fiber functor, does the endomorphisms of that fiber functor then mean something physical when there's the gapped phase?
So it corresponds to some. So in the particular case of the D8, graph D8, so we find there are 3 fiber functors. So there's an endomorphism, and that corresponds to basically the triality of the act on the 3 fiber functors. So it's some kind of.
No, sorry. So right. Okay. I meant like you have a fiber functor,
Yes.
which is just a functor from your category down to like the category vector space.
Yes. Yes.
And then just for that fixed fiber functor, you consider the endomorphism algebra of that fiber functor.
Right. That.
So for example, you start with rep G.
Yes.
Down, okay. This would be the non-conformalism reconstructive G.
But in that case, you just need domain walls between the different SPTs that correspond to the fiber functor.
Yeah.
Yeah. So as I said, there can be interesting edge states between these SPTs, but they're just domain walls in a sense.
Okay, so you don't have a general state. Okay, I just suspect that that's an interesting algebraic thing to look at. That should like be something directly physically meaningful in terms of that gap phase.
Isn't that always just A?
That's a good guess. I think. Yeah. Okay.
Somehow intuitively, it's like the symmetries which are preserved in that ground state, which like by construction we want to be the entire algebra.
So just usually I don't have a category. Or maybe just like the underlying algebra, underlying A, you mean?
Yeah, there will be some algebra object associated to the fiber functor as well. It's probably that,
Okay.
rather than the fusion category.
Okay. And you're saying it's always the same fusion algebra.
Maybe one quick
Yeah, that'll be Maria.
So I didn't quite understand the data of the fiber functor. Are you just adding topological defects operators?
So let me go back to that slide. So you have this single ground states. If you cut open the bulk with no defect insertions, and with defects you have this you have a defect reverse as I mentioned fixed. And then the additional data is defect 3.1.
last question.
Can you say something about the connection to 11 randomizers?
So the living model, as I understand, is a reformulation of the Torah theory. So in that case, you can realize explicitly that there are this SPDs that we have, or this generally the CFT, the fusion category symmetry as boundary conditions. But in that case, the fusion category symmetry is gauged.
Okay, so let's thank Deepak. We'll be back in 20 minutes.